Oregon public employees belong to a retirement system called PERS. The amount of monthly paycheck a person receives related to years of service, monthly earnings throughout the career, employees, and other factors. Distribution of payments is amazingly uniform distributed. The mean of this distribution is 450. M, I'm going to call this variable M, so I'm going to go E to the M. Keep trying using different variables so you realize I don't have to use X all the time. So this is the mean of this distribution, 450, and a standard deviation of, please remember to use the variable. That would be awesome. 2309. So we got our standard deviation and our mean. Now here's the first question. What is the probability that if I sample a person at random, a person, so I'm sampling one, that person would take 2,000 a month or less. So their income is 2,000, but I'm a single person, right? So what's happening is this is not about a sample distribution. I am just a question of the parent population. So this is the parent population. So the parent looks like this thing called uniform. This is called uniform distribution. And at the edges here is 550, 8550. And what I'm looking for is to make 2,000 or less. So I'm going to, again, this doesn't have to be exact, putting 2,000 here or less, and that's what I'm after. So notice the answer is this area. Just like in the other questions, the answer, is really the area right here is the answer. Now, when it comes to a normal distribution, I need to use some tech, or if it's not -1, -2, -3, some exact. But I need some tech to do this because I can't calculate the area of this curve. But this is a rectangle. The area of a rectangle is just length times width. So I don't need any special technology. I just need to calculate the area of this rectangle. But how do I do that? Well, look, the width, let's say this is called the width, 2,000 minus 550. Okay, that's the width of this right here. But what about the height? This part. So length times width, or width times height, however you want to think. It's just a multiplication of these two objects. Here's how to answer this question. Remember, this represents the entire population. So the area here is a 1. So if I were to multiply this height times this width, the answer is 1. So we've got height times width equals 1. If I want to know height, divide both sides by the width. And I got my height. The width of what? This width right here. So notice the height of this is what's sitting here. Take the entire width here, and take the difference and put it over 1. And that's what this is saying. So if I want to know, hey, look, what's the chance that my variable, in this case, M, is less than 2,000? What I need to do is height times width. The width is, again, this right here, 2,000 minus 550 times, and now my height is going to be 1 over this entire width right here, the difference again. So I need to calculate 2 different widths. 1 for the entire thing and 1 for the width of this rectangle right here. And when I multiply that, so again, now take the difference, I'm just going to come up. So again, find the difference, take the ratio of the 2, and what I get here is 0.18125. What's the chance that a single measurement is $2,000 or less? It's about 18%. Whatever happens if we sample 20 individuals at random? Okay, we're sampling 20 individuals at random. So now we're saying random. What is the probability that the mean monthly payment, back to the mean, so now this question is would be 2,000 or less. So same question, but now it's about the mean monthly of the 20. So this is a sampling distribution question. So what you should repeat over and over is this little process, just so it's really becomes part of your thought process. you're sampling what, 20 from these. And what are you doing with 20? Again, calculating the mean each time. So now you have this distribution. Hey, you notice how in this question, I never used the information we got about the mean and standard deviation because it wasn't needed for this question. It was just something that is the mean of this distribution, this is the standard deviation of this distribution. But to calculate here, I never needed it. But now here, I am going to need it. What is the mean here? At random, individuals means, again, unbiased sampling. If it's unbiased sampling, then that means that the mean of this should be the same as the population, which was 4550, and then the symbol for this number is E of X bar. So it's, sorry, not E of X bar, E of X bar. You had to think a lot more when you change variables. So this is EMM, the population mean, and it will be saying the same because my sampling process is unbiased. Oh, fantastic. And what will be the shape of this? Well, clearly this is what? Symmetric. No outliers. Really, because these uniform ones never have any outliers. They're just always nice and tight. And it goes 20. Yeah, what do we need? Or look at the criteria. For something like this, all we needed was approximately n greater than 10 would do it. And we got 20. So that's perfect. This means then that our sample size is big enough. So again, what I'm going to be invoking here is the central limit theorem, often abbreviated CLT. So central limit theorem, often abbreviated CLT. And now what I'm after is this being 2,000 or less here. What's the chance of gathering 20 numbers and the sample average being 2,000 or less? So I'm back to now to, once I know this is normal, again, how do I know it's normal? I'm using central limit theorem. I'm saying n is big enough for me to write this down. Okay, so now we're back to finding my z. So it's back to 2,000. 4550. So again, I'm going to do this. I can use the technology and come up with my number. And what's my standard deviation? Well, I need to take the population standard deviation, 2309, and divide this by square root of my sample size, which is 20. And when I do that, I get negative 4.93891. Okay, so this is not 1, 2, nor 3. So I'm not going to use any kind of 6895 because I can't. So what's the chance that my sample average is less than 2,000? That is equivalent to saying that when my z-score less than negative 4.9389, semicolon here, type less than, and now I'm going to go negative 4.93. And you notice that I'm going to just stop typing because it cannot show me anything. GeoGebra can only give you 4 decimal accuracy as output and to negative 4 standard deviation. Again, notice this is beyond negative. This is almost 5 standard deviations. So one thing I know for sure is that to 4 decimal places, this is 0, 0, 0, 0. That's what it's saying. Is there a non-zero value eventually? Yeah, there's definitely a non-zero value. But how far do I have to go? I'm going to guess like 7 or 8 places is where the first non-zero value is. So for all practical terms, this is 0. But to be more precise, I know that it's 0 to the 4 decimal places. In medicine, what happens a lot of times is that you'll say that this value, there's actually something else they do say, but we don't have the vocabulary yet. We'll say, look, this value, whatever it happens to be, this is 10, tens, hundreds, thousands, 10,000s. Then we'll say, look, it's less than 0.00001.